Good.
But I think even if I didn't publish anything, I could still ask for it
All right, let's begin. It's with terrific pleasure. I think almost everyone here knows Adi. He's a smart guy. He's been a terrific student of mine. It's been such a pleasure. And we're here today to hear his thesis defense. If you've seen the thesis on the table, there's no way he's going to talk about all of it, but he's going to do a good job to try to bite off an hour of it. So go ahead. Yeah.
Thank you, Jim. And all of this work would not have been possible without amazing guidance from Jim, from Antonella, from Sadid, with whom I worked at Philips, and also my friends Nick, Ryan, and Solomon. I'm just presenting their work here. Okay, so now this, I want to start with this idea of this deep learning or AI really taking off. And if you don't know what deep learning is, just think of AI, because as of today they're almost equivalent. They should not be, but they are. And we see all these fear mongering about AI is going to do this, is going to do that, and everybody's so scared. But when I see AI, I only see all the problems it has. I'm like, no, this is not going to take over. It has so many issues, and I will show you some of the issues today, and hopefully some of the solutions. But regardless, a lot of people are using AI for a lot of important stuff, including health. And the company where I'll be working also is going to do a lot of health-related stuff. And this all happened because this deep learning or neural networks went from this to this. Most of the people, when they think of deep learning as like some neural networks, but in real world it looks something like this. It's really huge, lot of parameters, a lot of computation, and when you put this humongous black box, it is able to do some amazing cool stuff. And but then this amazing black box, this huge black box, comes at a cost, and the cost is the amount of parameters in these networks is huge. It has the amount of computation these networks need is so much that you and I we won't be able to run these things in our own phone or laptops, even though we can do almost everything in our phones. They need dedicated hardware. And of course, companies like Google can afford it, but even they are burning money while running these apps. You don't realize them, but these companies are actually losing money when they give you these services. And the second thing, which a couple years ago people figured out, that these amazing black box, even though they are so good at doing what they say they are doing, if you tinker with them, they fail in a condition which makes them look ridiculous. And also at some point, it makes them look dangerous because people are depending on these technologies to work. People want like self-driving cars. You don't want these cars to be easily fooled, but they can be. I'll show you what that means. But just remember that this amazing success of AI comes at a cost, and cost is either it takes a lot of money to run these models, and it is not as secure as you think it is. So these are these two problems. And most of my thesis is wrapped around trying to solve these two problems. So therefore, so my thesis is mostly these papers and these topics, and each of them is trying to either make these models more efficient, that is, make them run faster, make them run cheaper, so that they can be run in a commodity hardware like your phone or even Google Glass. I don't know where it died, but it will come back. Trust me on that. Mm-hmm. And are trying to make them robust where you feel that you can trust these models. Now, I don't have the final solution in the sense I cannot give you a model onto which you can trust your life. Nobody can. And maybe we will never be able to. But at least we are taking a step. Who knows where it will be, but people are trying to figure out how to solve that problem. But as of today, it is still a problem. This is only a step towards that solution. And again, if some of these words don't make sense to you, it's okay. These are for the people who are going to sign this paper at the end. Hopefully they are satisfied with it, but it's okay. I will try to explain some of this. And I mean, other than these techniques, one thing Jim and I, we both agreed on that all this stuff is amazing only if we can show some real world applications, right? If I just make some cool algorithm and if nobody's using it, or if it cannot be used for some real work, maybe it will just collect dust. Therefore, with most of these papers, we try to add in some applications to it. And these are some of the applications. And now, not all these applications are necessarily tied very closely to the technique, in the sense you could use this technique to do other things too. And then there are other techniques that can do these things, but I will show you how these things can be done using the techniques we have built. And some of these things, you and I, we all know how it works, like image compression. We know how image compression works. Maybe we don't know how JPEG works, but we have a general sense of what image compression should be. And then there are other new AI-like tasks like question answering or paraphrase generation, right? And I don't know if you all use Google Inbox, where Google now actually suggests you what the reply should be. And these things are all trained using these sequence-to-sequence models. And I will, at the end, if time permitting, I will come to it and I'll show you how those things work. And the problem with that is, very soon people will realize you are using these shortcuts to send the reply, because all these replies look very homogeneous, very typical. They don't add flavor, right? If you are the one who always makes some grammar mistakes, that algorithm is not going to add in the mistakes for you. And people will figure out it was not you. You are too lazy to send them a personal reply. So we are trying to work on paraphrasing, right? That is one idea, where can you paraphrase this right answer in a different way? Is there a style? So we will come to some other things on how we have tried to solve this. And again, we first saw that existing techniques are great, but they fail in certain scenarios where they are too big or they are not robust, and we'll show you techniques to make them more efficient. Okay, so let's start with the very first one, which is also latest work, and probably most of you have not heard from me about this, so probably I thought this is a good one to start, because maybe at 4:30 if you had to leave, at least I would have given you the most I can. Okay, so this is called as RePr, and we'll come to why it's called RePr later on, but the idea is we want to train these neural networks to be efficient, right? A couple slides back I showed you that the modern networks, they look huge, they look really big. And the idea is, can we make them smaller so that we can run them on our phones? And it turns out, yes, you can. There's this idea of pruning deep nets, where you just go and play Fruit Ninja on these deep learning models, and you'll be surprised it works. It works that the number of papers doing this is so many, it's hard to keep track. People taking existing black box models and saying, where can I chop off and make it smaller and make it efficient? And there are many ways to do it. But the general idea is, you take a network and you figure out what is not useful and you remove it. That may or may not make it faster. Sometimes it makes it smaller but not faster, but that is semantics. Okay, so the question is, why do we do this? Why don't we just train a smaller network, right? What's wrong with that? Why do I have to take a bigger box and then chop it to make it small? And the answer lies in this one clever graph. In this graph, again, there's too many lines, too many things. Don't worry if most of this doesn't make sense, but the only thing to remember is, if you take some model, right, let's say some number of parameters, some number of values, you will get this amount of success, right? And here that success is like 22%, 23%. But if you take a model that is twice its size, right, and you learn it, you get amazing success, and then you can take this twice the big size model, start chipping off the unnecessary parts, and then you can get up to this success. So you can see here, all these models on this line, they have the same success, and they have the same parameter size, right? But they have different amount of success. So why is it the case that we can take a bigger network, make it smaller, and yet it is so good, but we cannot take a smaller model and train it to be as good? And again, nobody knows this answer. Jeff Hinton certainly doesn't know the answer, right? But people have intuitions, people have ideas, people have techniques. Sometimes techniques comes before ideas, and sometimes the other way around. But I'll show you one of our ideas. Again, that is not the universal way to do it. There'll be a lot of people who will say, that doesn't make sense. Luckily enough, at least 3 people agreed that it made sense, so it's accepted to CIFAR. But who knows? Maybe there's like 99% of the people don't like this idea. But you guys be the judge at the end. Okay. So the idea with the pruning, in order to understand our technique, we have to understand how this pruning works. And here I'll go into a lot more detail. And if you're not in this field, this is the time to grab a sandwich. So the idea is, you take your model, you initialize the weights, and then you first train it. And then after training the model, you open the box and see, and think of this as like a big box with a lot of marbles, right? And your training is like you are seeking this box, and these marbles can go into specific places. And then when you open the box, it makes a perfect, like a perfect picture. And then the idea is once you open the box, you want to see which are the marbles which didn't really add to this picture, this diagram, and you want to throw these marbles out. And that technically we call it as neuron ranking. That is, you're trying to rank the filters or the weights to say this filter is not really useful, let's not have them. And then once you do this, you retrain the model with whatever smaller size you have. And this retraining of the smaller model is important. And this is important because this is the key to some of our clever techniques. And if you don't do this part, you will not get a great success. You can't just chop off the existing model. You have to, after chopping off, you have to give it a chance to relearn what it has lost. And that is very important to our work. Now, so in this, you'll realize the critical, everything else is very trivial. The critical part is knowing how this parameter importance works. See, because I said we open this black box, right? Isn't by definition of black box that you cannot see what is going on? And that's true. You can't really open this black box and peek and see what is going on. Therefore, you have to look at the box from outside and then be a judge of which of these parameters are useful and which of them are not. So one way to do is, okay, let's take this neural network, right? Let's remove this one parameter from that neural network, take our data, train the model again, and see the performance, right? So just without that one extra value, what's the performance? If the performance is a lot worse, you know that's the important one. You can't afford to lose it. And sometimes the performance will be higher. There you go, you have a freebie, right? You can throw that and not worry about it. But as you can realize, this is going to be a lot more expensive, right? Like I said, remember, these neural networks don't look so small and trivial like this. Neural networks look a lot bigger than even the ones I showed you there, right? The screen only goes so far. It goes all the way to the downtown. And so we cannot do this. So one shortcut is, let's remove the training. We take an existing network which has already been trained, right? We freeze it, we don't train at all. And now we turn off a specific neuron or a weight or a filter and see how much the performance goes down. Now here, either you will think, oh yeah, that's totally fine, that makes sense. Or you will think that's, okay, my mom is here. And it doesn't make sense at all, right? Because this network was trained with all these parameters. You can't just randomly turn some bulb off, right? The whole thing is designed to work together. But anyways, this is a cheaper version of the oracle. So therefore we call it as a greedy oracle. It is not the best solution, but this is what we can afford, right? And similar things goes in politics, but I'll leave that to other people. Okay, so this is what is a greedy oracle, and we will use that to see what is going on in the network. And now, if you do that with a very, very, very small network, and here I intentionally picked a small network, because if I tell you that this network had billions of parameters and a couple thousand of them were useless, you're like, yeah, yes, that's true with everything, right? When you have so many of something, some of it are not as useful as others. Classroom, your students, you can put anything in there, right? But even for a smaller network, which really cannot afford to have some parameters slacking and not doing their homework, even in those networks, there are a lot of these things. So here the x-axis represents how much will your accuracy go down if you were to say bye-bye to those filters. You can see a lot of the filters are between 0 to 1 in a network which has only 64 filters. It means a lot of the filters don't want to do any work. And this surprises us because there are a couple of guys doing the heavy lifting. So now the question to ask is, are these two related, right? This is a small network, and this black arrow is a small network, and I'm telling you that small network doesn't do as well as a big network that is made smaller, and this is a peek into what happens with a smaller network. Are they related? Can we combine them to somehow do something about it? And turns out, yes, they are related. And one of the motivation is the reason, and people try to explain this reasoning that why it is easier to train a bigger network, make it smaller. And the idea is called a lottery ticket hypothesis. It's a hypothesis, nobody can prove it, but that doesn't stop people from taking this as the gospel and write a whole paper and give a PhD defense on it, but I will attempt that anyways. So the idea is that when they say that if you have a lot of parameters while training, you are learning this ensemble or combinations of this, a lot of mixers, right? Each time something is turning off, something is turning on, and you are learning this combination or like combinatorics of this model. And therefore, in that way, so what they're saying is, yes, there are smaller networks that can do the job, but it's very hard to find them. But if you start with a lot of things, maybe some of them will be lucky enough to really get that lottery, and the others, they are just slacking. But initially, you don't know, right? So you want to start with as many tickets as you can, and then once the lottery is drawn, you don't care about the tickets that never give you any winnings, right? But if you know that you got a winning lottery ticket, and that's the idea here. Our idea is, yes, the network has a lottery, but in order to maximize your winnings or maximize your winning chances, you want to start with as many lottery tickets as you can. But then, of course, that works. People have shown that. But we don't want to do that for various reasons. Why? Because this is a lie, right? When I said this has 50% parameters, so I tell you that, oh, this model has same number of parameters, that's true. But that doesn't mean these models run at the same speed, right? Because with deep learning, one of the idea is if you have a lot of layers, so if I tell you that you have two networks, one has 10 layers, one has 10,000 layers, and both of them have same number of parameters, that doesn't mean both of them run at the same time, right? So some of these researchers, they will hide these details. There's okay, let's not use another profane word here. So they'll hide this detail. That is why we care about starting with a small network, which you know how fast it will run. That is why we want to do this. Therefore, we don't want to start with a lot of lottery tickets. If I told you that for the next lottery thing, you can, as the lottery numbers are being revealed, after the first number is being revealed, I will allow you to exchange all your lottery tickets for free. How wonderful that would be, right? Who would not play lottery, right? As soon as the first number is revealed to be 1, and you throw away all the lottery tickets that doesn't start with 1, you go and buy all the lottery tickets that start with 1. You improve your chances, and you can keep doing that until the final number. Maybe except the final number. There's no anything after that, right? If that were possible, the chance of you winning the lottery is very high, and that's our idea. That is, we start with a smaller network, and as network is training, we find these bad filters, and we throw these bad filters for an exchange for possibly a good filter. And I say possibly good filter because there's no guarantee that the new filters will be good, but at least we know we know that the ones we have are terrible. So we'll do that. So this is our key insight. Again, this is a lot of mumbo jumbo just to say that not every parameter is equally important. Not everyone is a good guy. There are some slackers. It's time to boot them. And again, this is the step-by-step instructions of that. Again, this is similar to what we saw before, except instead of dropping them, we are reinitializing them. Right? We are saying, you did a bad job, go back to first grade, restudy whatever you learned, and come back and do a better job. And that's the idea. It might sound ridiculous, but that's the idea. And that's why we call it RePr, because it is reinitializing the pruned filters, and then it is pruning some of the filters. Why is it not called per-re? RePr is easier to remember. Okay. So that's the idea of the trend. And if you see here, this is so here the orange curve shows what a normal network training looks like, right? And this is a training accuracy. You should never rely on training accuracy results, but I will do it anyways. Because the point I'm trying to make is only visible on the training, right? Because you're trying to let the model do some task. Therefore, the orange curve goes up, no surprise. That's what it's trying to do. And the blue one is we're saying after a certain point, we will throw away some of the slackers. And when I say slackers, that doesn't necessarily mean that they were doing nothing. They were doing something. That is why once I drop them, the model is worse than what it was. And then for a brief period, I will let other guys catch up on things that were missed. And they do catch up some of the lost information. And then when you bring back these dropped guys with new set of weights, they are able to maybe not get the same performance, but they do better at task. Now you will say, wait a second, isn't higher accuracy better? Looks like we did worse. Why am I showing you this? Because in the real world, we don't care about training accuracy. We care about the test accuracy, the test performance. And this is this idea of generalization. Some of these networks overfit so easily that Just because a network has a better training accuracy doesn't mean it does better in real world. Real world means, so Facebook can take all your uploaded photographs and train a facial recognition, but it cannot use the models, train those to classify some of the private selfies you take. Why? Because you have never uploaded some of these photographs to their server. They don't have that training data. So there's a disconnect between test and a training. And that is where the magic comes. If you look at the test performance, blue line is higher. Thank God. I mean, all this would have been wasted effort. So it turns out that generalization improves if you do this. And again, am I sure that it is the lottery trigger hypothesis that's the right explanation for this? No. Do we have a better explanation? Sorry, my PhD time ran out. Maybe somebody else will try to have a better explanation of why this works so well. Okay. So now all this is so great, but I told you about this greedy oracle, which I said is better than doing a full oracle. But even greedy oracle is not a feasible computation to do on these networks with billions of parameters. You cannot turn off one parameter, do a full run on a validation set. It is still a lot of computation. We want something where you don't have to turn one parameter at a time. And here starts the quest of finding something which is as good as oracle of the god, but it's cheap. And again, this search has been going on, right? Even before neural networks were cool, even when our department chair was doing neural networks. At that time, people were saying, can we find this magic function which can take a neural network and tell me the bad guys? And people have been doing this all this time. And everybody has their own reasons to believe what's the right function. I have my own reason, and I'll tell you what my function looks like, but just so you know, I'm not the first person to attempt this impossible task. So second motivation comes by looking at what these neural networks are actually doing. Right? So if you look at these guys, these filters, these neurons, and see what kind of information they're trying to capture, right? You want all of these guys to do their own thing so that in sum you are doing a lot of things. Right? If you find out that two of the guys are doing the exact same thing over, you're wasting some of your valuable manpower. And it turns out that's what is going on. Here in this graph, if the color is light yellow or bright yellow, and if you're colorblind white, then it means there's two guys who are doing the same thing. That is, you could kick the one guy out and you would not lose any information. You don't want that. You want this to look like complete dark blue. Of course, in heaven it does, but not in the earth. So the idea is, can we do something about it? And so what I'll do is, I will try to penalize the network for having too many bright lights. Anyways, I like dark themes in my editor anyways. So let's do this. So again, the mumbo jumbo is called as minimizing the directions captured by these filters. This is only for the 10 people who understand that sentence, but for others, we want to turn the lights off. I think I will yawn with all that mumbo jumbo. Let me show you this in a more pictographic way. The idea of ranking is, if you think of A, B, C as your three guys, and the reason one of these guys already looks like a bunch of other guys is because in CNNs we talk about filters. We don't talk about a single, so individual box is a weight, but there's no benefit by dropping a single weight, because in CNN the conversion has to be done at a filter level. If you drop a single weight, you don't get any benefits of a smaller network. So we try to treat the filter as a norm. So this is our one guy. So the way we try to find the ranking for A, B, C is, first again, this is a 3 by 3, it's hard to deal. Let's flatten them to make it one long vector, right? A bunch of numbers in a sequence. Then we take the same sequence in a transpose, and there is magic which happens when you multiply this in transpose, and you get this unique kind of matrix. This matrix represents the correlations between each of the units. Right? And then once you get that, you don't want the correlation of the same unit, so the diagonals represents correlation of A with A. We don't want that. So we remove the diagonals, then you get that matrix and you sum all the rows, so you have this same ABC, which is one single number. So you have reduced a filter to one number, and that number is what I'm calling as the ranking criteria. That's the magic number that tells you how good or bad it is. right? And I'll use that to drop the filters. So now question is, how well does it correlate? Here, correlation with the God or echo. If it is 1, we can pack our bags, go home. Unfortunately, it is not 1. In fact, it is not even so good. It's barely better than just taking the size of the weight. If the weight is big, you keep it. If the weight is small, you drop it. If you were to simply do that, that already beats a lot of the accepted papers. So just so you know, for the new PhD students, the bar for publishing is not that high if you can convince people to not look at the simple ideas. That's where the magic is. But anyways, we are better than simple ideas, so at least there is something to it. But it's not that good. But then the thing is, this is, again, for people who understand statistics, this is Pearson correlation, correlation of the values. We care about the correlation of the rank because you are going to use the rank to drop the things. When you do the correlation over the rank, then you see the money shot, right? And there you see there is a real benefit of using our ranking, which is called as author, compared to anything else. Okay, at this point, I think I'll have to slightly speed up. Again, these numbers, don't worry. If it is higher, we are doing better. That's all you need to know. So the final solution to this problem of taking a smaller network and making it as good as a bigger network is these two things. And now, this is before, this is after. And no, unlike the infomercials, I didn't take the after picture before the before picture. So, yes, there are still some lights. We could not get rid of all of them, but I think we did get rid of most of the lights, and that's a good sign. And because of that, so now here, I'm trying to normalize the accuracy of different number of layers, right? So if a 3-layer network got some accuracy 70%, we'll call it as 0. So anything above this line is good. Anything that is below this line is bad. So not only our technique is good across any number of layers, our ranking is also better than other ranking. So combining with both our technique and our ranking, you get amazing performance. And again, this is how many filters to drop, all these things. The details are in the thesis. I'll skip these things, but I have an answer for how many, how often, all of these things. They come from a lot of hyperparameter search. Thank you, big corporations, for giving their GPUs. And again, if you don't understand dropout, don't worry about it. I'll skip this for lack of time. Only thing you have to remember is, so ResNet is a very popular neural network, and it is almost like state of the art. Not because it's state of the art, but because it's so easy to use and close to state of the art. And as you go deeper, you go better performance, right? So ResNet 34, so this is error, so lower is better. So ResNet 34 is better than 18, 50 is better than 34. So with our result, don't worry about the numbers. All you have to remember is, with our technique, 18-layer ResNet is better than 34-layer ResNet trained with standard techniques. And that's the only thing you should take. So that's it. And we have also good results in VQA and object detection. And so in summary, some of these neural networks, the reason they don't perform so well is because multiple filters try to capture the same thing. We are telling them not to do it. And that in itself does amazing. Okay. So now that we are done with RePr, let's get to pixel deflection. Let's get to robustness. We looked at how to make a network faster, and making network faster not by taking a big network and chopping off some of the weights. We are making them faster by starting with a faster network and making them as good as the bigger networks. Right? Okay. Now let's worry about the robustness. Like I said, now some of you have seen this slide. I have taught this class multiple times, so you know what this is. This is a picture of an elephant. That's the same thing, at least to my eyes. If there is any aliens here, tell me if you see something else, or any Skynet bots here. But to human, these two look the same. For a machine, the other image does not look like Indian elephant. Why is the case? And the only difference is some garbage here, and that garbage we cannot see. And it turns out, the way to do this is a typical block diagram of a neural network. And there is some loss function in the end which tells you how to tune these parameters. And generally what you do is so while tuning, you tune all the layers except your input. That's always given. But if you go one step more, why not, right? A kid always wants to try something which people tell you not to do. And so I don't know if someone by accident did that, but when that person accidentally tried to add that to the input, he got these weird results. And then the whole series of research started, where people can find small changes to the image that can fool neural networks, but not humans.
We targeted too.
Yes, and can be targeted. You can take the image of Indian elephant and make it Jim.
That's not much work.
Yeah.
But you can also make it guacamole, or you can make it right.
Exactly. And but the idea is, and this is an example of one way to do it. There are other ways to find ways to fool these neural networks, and there's some of the ways are even amazing, and some of them are even harder. Some take longer time, but they have their own ways. So that's just one example. And now question is, okay, if there are ways to fool the network, there should be ways to prevent network from being fooled. And one way to look at it is, yes, either you can make a better models, right, which is always the solution your parents tell you, right? Just study harder, right? Make a better model. But we all know that's not always the case. Who's going to play Smash Bros? Right? Or you can say, if this adversary or my enemy is adding some bad stuff to my image, can I find this bad stuff? Maybe human eye cannot, but maybe there's something in this thing I can find. And turns out that's also hard. People have tried and given up, or maybe they have not given up. Who knows? But at least I didn't try, because that didn't seem the right direction. One way is, we'll say, okay, these people have added something to our image, right? And I don't see the difference. And maybe I can tell the neural network to not see the difference too. Who cares if there's something added? And again, that's a very broad way of saying what I did. But the idea is, you also do something to the image, and hopefully you cancel out what has been done. And what you do doesn't impact the actual performance of these models, this black box. And this is a category of difference called as image transformation. And this is where our work, pixel deflection, lies. So the idea here is, I'll skip this. Okay, so the idea here is, it turns out if you just do a simple JPEG, so this is the image, and this is the image where the neural network thinks it's a guacamole. And if you take this bad image, if you do a JPEG image comparison, it turns out the right class returns. But the confidence is very low, and not always. Its performance is good, but not that great. We want this to be a very flat line at the top. We don't want this to go down. But so as you increase the compression level, maybe it recovers, but also the compression adds its own noise, and it's not ideal. So we want something better. And people found this out by chance, but we want to do something better than JPEG. Okay. So one thing I want to show you is these classifiers, right? They are robust to noise. That is, if you take a natural image, and by mistake, instead of actually sending the image, you are in 2019 you decided to print that image and then take a photograph and then send that to your friend. Some people do that. You'll be surprised. Then that classifier can still look at this rescanned image and still tell you if it is Indian elephant or not. That is, the classifiers are robust to these natural noises. They are not robust to these adversarial noises. Adversarial means when somebody is really trying to get you. See, so many people are worried about, oh, my social security number has been leaked. Come on, if anybody's trying to get you, they can get a lot more information than that. So don't worry about all these Equifax data leak. If someone's trying to get you, they will get you. And that's the idea here. If they're trying to get you, they will get you. But if the noise is naturally occurring, you don't have to worry about it. I'll show an example, right? This is that image of Indian elephant. Right now it's classified correctly with almost 98% confidence. And I will start adding some random noise, right? 10 random noise on this big image. You can't see what the noise is, but when I add more and more noise, maybe you'll be able to see these salt and pepper dots. And you can see here, the class still remains the same. So now you can see this image already looks very bad. You and I will be able to see this image and say, something is wrong, right? Somebody did something terrible. But then we don't know what the terrible is, and it doesn't matter. Neural network still thinks it's Indian elephant, right? Even at this level. And now let's take an adversarial image. The image which your enemy or your ex added some information and make it guacamole. And now when you add just 100 random noise, already the confidence of guacamole has gone down significantly, and Indian elephant is peeking around the corner, and just with 1,000 random noises on the adversarial image, we get back the original class. So adversarial images are not robust to these noises. So it seems maybe we have fixed the problem, right? What is there to do more? But again, like Jim says, in papers, if they show you some result, remember that's the best result they could get. Right? This is cherry picked. There are the hundreds and thousands of images where if you did this, it would not work. And there's no point in showing you that here, right? So the idea is maybe there is something here, but it doesn't work all the time. And you want something that works most of the time, if not all the time, right? We'll be pissed if our internet went out as often as it does in my home country. Oh, so trust me, my mom is sitting here. She's like, I've been calling you for 2 hours. Like, I never got your call. Okay, so, and the second key insight we have, again, I told you the first key insight, adversarial systems. That's bad guys, they cannot handle the noise, but we don't know how well. But we'll come to that later. Second thing is, see, these bad guys, they are blind, right? If they are trying to make quick buck by faking your ID and profile, they don't have to find you. They'll just find one person, right? So this is like the saying, I don't know if it's a folklore or it's a real saying, that you don't have to be the fastest deer in the wild. You just not have to be the slowest, right? So the idea is the same. These adversaries, they're going after the easy targets, and it turns out they are blind in the sense they don't really know where things are. And again, this is a very technical for this audience, but there is one way to find where the neural networks are looking at, and that technique is called as class activation map. Right? You can take this neural network and do some math to give you this kind of a map which says, okay, if this neural network thinks that there is an Australian terrier, probably it is looking at this area. That's where the Australian terrier is. And that makes so much sense, right? Yes, that is where it should be. But trust me, in machine learning, you cannot just take that assumption, right? If you're given the whole image, why should the image rely on these pixels, right? If every picture of Australian terrier had the same guy, neural network would think this guy is Australian terrier. And there's this whole story about the tank problem, which you should look it up. So the idea is, yes, there is a way for us to see where the neural networks are looking at. So what we did is, we took a lot of images. I mean, I say a lot, couple thousand. There's a lot. And then we averaged where these neural networks are looking at. And no surprise, the average area of object is in the center. Because even though we might not be great at photography, or we don't know how the lighting works, at least we are good at putting the face in the center. At least that's the basic we are good at. So it turns out most of the content is in the center. But if you did the same thing, not with the natural images, but with the noise added by the adversary, image looks like this. And again, if this image doesn't make sense, think about all the average changes which the adversary has done, all the changes, and if you average across several images, it looks like really they are going after any pixel that can be fooled. Like I said, they don't have to fool the toughest guy, right? They'll go for the easiest pick first. So there is some difference between this and this, right? And in maths and statistics, if there is some way to tell the difference between A and B, you should use that. And that's what we're going to do. We'll say, if the distribution of things looks like this, probably it's a good image. If it looks like that, probably it's a bad image. And so what we'll do is we'll combine these two key insights about adversaries not being robust to noise and adversaries not looking at where the object is, and we'll call it a pixel deflection. It's an interesting word. So Solomon Garber should get all the credit for coming up with this clever word, and this is our idea. So the idea is, again, there's a lot of math here, but the idea is you take a small box in the image and you replace the pixels of the same box. And there is a reason we are just replacing the pixels of the same box and not adding a noise from outside. Because we want to keep the distribution or the local color scheme, let's say, same, right? Because this image shouldn't have any bright pink images unless there is something relevant to that. So we want to keep the local distribution, local color scheme same. And the reason we are changing the pixels is because we're adding noise. That's the kind of the noise which adversary is not good at. So when you do that. Now the only difference is you do more of it in the background and less in the foreground. And who tells you what the foreground background is? This image tells you where the foreground background is. And again, in this particular image, it looks like everything is in the center, but for any other image, it could be somewhere else. Right? This is an average. So if you do that, that is, if you do more of pixel deflection on the outside and less on the inside, turns out that, here the map tells you that this neural network thinks elephants should be somewhere here, so you do less of the noise here and more of it outside. It does, and just this idea does amazing. But before we call it a solved problem, turns out how do we get these maps? We get these maps from a neural network. So if a neural network can be fooled to say say an Indian elephant is guacamole, it can also be fooled to say where this aeroplane is. Because now if you see, if a neural network which has been fooled thinks this aeroplane is here. And again, in this case, because I have told this neural network to think it's a meatloaf. I don't see the meatloaf, but I know some people who dream about meat all day, all night, so probably they do. So in the same way, this classification map can also be full. And then, so at that time, we had to pause this research, do a whole set of different research on how to fix this problem. We wrote that paper, we got it accepted, came back, and then tried to solve this. That is how it should work, but that's not how it works in grad school, right? You do all things at the same time, right? So in one go, you get 2 papers. And that's what we did. Don't worry about that graph. There's a trick we can use with multi-class classification. Okay. So we did that, and we call it as a robust CAM. And you can see a robust CAM, even though this image is classified as flat worm, it correctly picks where the airplane should be. Right? So we have fixed that problem. So now we can combine those 2 things and do our magic. And now wait a second. So we are adding our own noise, and we know it will work if image has been manipulated by some bad guy. But most of the images will not be manipulated by a bad guy. And you don't want clean images or real good images to be impacted. Right? A solution is not a solution if it works when you don't know, or you don't know when it will work. Right? You want a solution when it will work regardless of what the input is. And the idea is you don't want this curve to go down for clean images, and you want this to go up for bad images. In the ideal world, this would be a straight line, and this would be a horizontal line, this would be a vertical line. But like I said, after Trump, we realized this is not ideal world anyways. So it is good enough. As long as this blue-green is higher than the red, it is good. So for both clean and for adversarial images, we can get the right class. Not with the same confidence, unfortunately, but with high enough confidence that we can rely on it. And again, this is a lot of numbers to show that, yes, our paper is worthy of acceptance, but the only things you have to remember is most of the time the bold figures are ours. I wish I could put that down there, but these guys did an amazing job. Okay, you can't win it all, right? Like the famous philosopher Mick Jagger said. Okay, so in the summary, we have 2 key insights with the pixel deflection. 1, classifiers are good with noise, but bad guys are not, until they figure it out, right? Again, tomorrow somebody will make an adversarial system which are good with noise, and all this will not work. And I'm hoping to get my thesis done before that happens. And the second thing is classifiers are blind, and the same rules apply. And our solution is we add our own noise, but we add noise differentially so that we know we are not blind. Okay, so now that's the second topic. I know it is a lot of content, but what can we do? It's many years of work in an hour. And the second paper, third, I don't know which number it is, but paper was, now we want to say, okay, we did a lot of techniques. Now let's do some real work. Let's benefit the world for all the research we have done. And one of the ideas which we have always toyed with is, can we improve some of the existing techniques with some of these cool deep learning ideas? So if you go back with the CAM, right, CAM was one idea to tell you where the objects might be, right? At least one main object. And that is what CAM is. CAM is like, if this neural network thinks it's a dog, I know where the dog might be. But the problem is, first somebody has to tell you that there is a dog. How do you get that? Isn't it a chicken and egg problem? How do you know what the objects have? So we wanted to make a CAM-like thing where you don't need to know what the object has. CAM will just highlight everything that might be a real object. And when I say real object, a selected list of things. And the idea is, like I said, CAM is good, but it only really picks 1 or 2 salient things depending on what class you think it is, and doesn't do all the objects. So there is a problem. That is, CAM identifies a single salient object, and we wanted to find all the objects. Why do we want to find all the objects? I will come to that in the next chapter. So first, let's fix this problem. how do we find all objects? Simple. A CNN has a set of filters, and it trains to find some specific class. And instead of one class, you want to find 6 classes, have 6 set of filters. So trivial and simple in explanation, but the math is hairy, and I will leave that out. But the idea is, yes, you can group these filters and train them to learn separate set of things. And again, this might sound familiar, because with the RePr, we're trying to say all these filters have to do a different task. But at that time, we didn't care what task they were doing, as long as they did different tasks. Here, we care what task they are doing. In fact, each of these set of groups, we are telling you to do one specific task. And again, this is some simplification of the work, but here you should think of a group of these filters saying, I will always try to find where the elephant is. And the other set of groups saying, I will always try to find where the person is. I will always try to find where the mountain is. And again, these are black box, in the sense we don't know for sure that is what is happening. But that is what we tell the model to do, and that is what the result we get. Right? You might say, yeah, 2 plus 2 is 4, right? But may not, who knows, it may not be, but because we cannot guarantee. Okay, so the idea is we'll have a set group of filters. But now, there's another problem. The problem is the types of objects can be large, right? Especially the data set we use, ImageNet, that has 1,000 classes. So 1,000 means if you had 500 filters before, now we have 500,000 filters. And my whole pitch of the PhD is, let's make smaller and better networks. I can't have a separate chapter where I say, oh, by the way, for this time, just forget about what I care. I have to keep it small. So one trick to keep it small is to look at the classes, look at things, and to realize that these 3 things may be different classes, different breeds of dog, but overall their geometry, their shape looks similar. I don't see, because for our task we don't care what kind of dog it is, as long as we get all the area of the dog. And I will tell you why that is, but we don't care if these 3 are the same class. So we will group a lot of classes together. And a lot of hand tuning was done to group those classes. Unfortunately, I don't have a magic solution for that. And of course, I had to spend some relaxing months also, right? I can just be doing intense coding. So in the cold mountains of Utah and snowboard, this is what I was doing, if you're curious. So once we did that, once we reduced the number of classes, and for the early filters, we said, first couple of layers, we don't care about the filters. And again, if you know deep learning, you will realize that early filters are Gabor filters, edge detectors, they are common. But higher level filters, we care. So at that time, so when we combine these 2 things, you get I wanted to call MS CAM, but we can't call it CAM, because CAM means class. We don't know the class, so we call it region of interest. And multi-structure, because every important thing that could be of importance semantically should be highlighted. And so far it looks like it's good enough. SpaceX, right? So that's the idea there. So we got all the people, and we got the arrived. And now question is, why do we care about this specific kind of heat map? Who in their wild world is going to need this? So now the thing is, you have to invent a way to use this, otherwise the whole point of this was useless. And we did figure out how to use that. And for that, what we do was, we say, we will make image compressions smart, right? Everybody's saying, AI with your food recipes, AI with your cars. We say AI for your JPEG image compression, right? And everybody knows JPEG, right? We always need more JPEG. And the idea is, but JPEG has a problem, although as universal as it is. One of the problem is, like our adversary, it's also kind of blind. In the sense, every block, every pixel it looks at, it's just doing a bunch of numbers. It doesn't really know what the pixel has. It knows some information about frequencies and who knows what, but it doesn't really know where the dog is or where the cat is. And you might think, why do we care? As long as JPEG works. We care because, like most things in the world, there are trade-offs. And trade-off is either you can make a small size image so that you can send to your grandma who's still using a flip phone, or your friend, but or you can make it really look good, and there's a trade-off. But if we can make a smaller image which really looks good, jackpot, right? And that is why we care. We care about making JPEG better. And the idea again is, let's look at this image, right? Surely when you looked at this image, and sorry for the people who are looking at a very wrong angle, or maybe I'm blocking you, but there are some salient reasons, and your eyes will pop or will really look at some reasons at the very first sight, and most of the time you're only looking at those reasons. And the idea is this image has been compressed with same kind of quality all over, even though your eyes is only cares about some areas. For example, I don't know, for Jim and for me, it was this specific box where our eyes went first. And we're like, maybe if our image compression was smart and made this image where this box was really high quality, and maybe these regions were bad quality, maybe a lot of people would not care. Right? So we're trying to distribute the qualities. Think of image quality as a finite sum of money. Right? You are trying to pay these people. In our RePr, we're trying to tell everyone to do this equally good job. Here, on the other hand, we're trying to find some place where we can pay more money, that is more quality than the rest. And again, it's a sneak peek, but our method does that. It surely looks better, right? Let's jump in. So the problem is, yes, we can make a new kind of image compression technique, which will do all this fancy stuff, but who will use it? Do you know, have you heard JPEG 2000? Yes. Do you use it? Anybody who raises hand other than Jim will surprise me. Right? There are better techniques than JPEG image compression, but nobody uses them because JPEG is widely used and we are in the loop. We are stuck. Everybody uses JPEG, therefore you have to use JPEG, and because you use JPEG, your kids will use JPEG. Right? So because we're stuck in the loop, we want to get away with both. We want to improve image compression, and yet we want to stick with JPEG. It's like, trying to debug code from 60s or 80s. You have to use this Fortran code, but then you also want this new advancements. And the thing is, it turns out there is a clever trick you can do. And this trick, it seems trivial to me, but I'll call it clever because it took me many tries to explain this to people who care about this sort of stuff. And after doing this trick, you can get away with both. You can have a cake and eat it too. You can have a JPEG image, which is smart in the sense it knows where the things are. Okay. Let's see how it works. Okay. This is a JPEG pipeline. Don't worry about all the mumbo jumbo in the boxes. You only care about that there is a knob. With a JPEG, you can turn the knob, and if the knob is at 100, you get a good quality image, but it's too big to do anything with it. The knob is turned all the way down. It is as bad as what Ryan sees every day. But you can combine this, you can do this clever trick with a knob. And the idea is to do it twice. Once with good, once with average. And the idea is when you do it twice, different regions combinedly get different combinations of tuning. Okay, let's see how it works. Get your standard image. Get your MSROI. No cam, right? It doesn't work. Now, if you look at the specific region of MSROI, again, this is called as a heat map because it means values go from 0 to 1. Blue means bad region, we don't care. Red, hot region, we care. So now we bin them between the things we care, things we don't care. Things we care, we do a JPEG compression with a high quality. We turn knob all the way to the good. Things we don't care, we do with bad quality. Put them together, do a second round of JPEG with one fixed set of quality, and in the end, you get an image which is a standard JPEG because it has gone through one last round of JPEG. It knows how to be decoded, and this image is somehow good in some places, bad in others. It is good in the areas where the heat maps is high and bad in the other regions. And that is the idea. And it turns out, does it mean we have broken the rules of physics? We have more money than we started? No. We still have the same money. The PSNR, the overall quality, has not improved. It's just that we have redistributed the quality to the areas we care. Right? So the quality where we care is better. It means surely we are worse in some areas, but that's the trade-off. Okay, and again, this is the only box we keep. So in summary, now surely we are paying for this, right? We are paying because we need big fat GPUs. And again, RePr came after this, so no RePr here. But we need big fat GPUs to do this computation of CAM, MSROI, and then to combine them. But the good thing is, and I don't want to use the air quotes here, but maybe I'll call it pending trademark. Our image can be decoded with off-the-shelf JPEG decoder. And there's a reason I call it pending trademark. So try Googling that phrase, off-the-shelf JPEG decoder. And the good part is, you see, in all this process, we don't really rely on JPEG in itself. In that step where we're combining, we could have replaced that JPEG with JPEG 2000, and you'll get a better JPEG 2000. But it's like, trying to make better black metal music. Maybe some people care, most people don't. Okay, now maybe I have a little bit time for one more paper. Again, this is only halfway, but lucky for you, a department doesn't give all day for this is difference. You are saved. So one amazing work we did, and this was amazing because at that time people, again, this work was several years ago, so it might seem like everybody in NLP knows how to do sequence-to-sequence modeling or paraphrasing or translation. What are you eating? What but that year, no one knew how to do. Some people knew how to do some sequence-to-sequence modeling. People didn't know how to do sequence-to-sequence modeling with paraphrasing. And you said, isn't this the same thing? It's not. I'll tell you what. So this is a typical neural network that does sequence-to-sequence. So given a sequence of text, it outputs a sequence of text. And generally, most of the machine learning techniques, machine translation techniques, use this. You give in a French, you get some garbage out. Right? I mean, it works great for some languages, not so great for others. But anyways, it's a good progress. And you might think, then why don't you give English here and English there? But the idea with this neural network is all of the content, the semantics of the sentence is, squeezed into one small space of information. It means you have extracted the meaning out of a sentence, and from that meaning, you want to regenerate the sentence. So it works great with translation, right? Because every sentence is saying some information. If you have captured that information, all you need is a new set of domain, and that domain and that meaning will give you the sentence in that language. If you do with English to English, what happens is whatever was the input, it gives you the same output, right? Because that is the sentence, which means that we're trying to capture, right? It seems so trivial, but that is a problem. You cannot trivially do this kind of modeling for monolingual translation, so to speak. So what do we do, right? So one of the solutions is somehow we want to maintain the domain. So one way is, can we skip converting some of the information that is trying to bottleneck the information, right? Because if you're trying to extract the information, you leave out some information. And it might not seem like why that is useful, but turns out that is useful. So we call it as skip connections. And at that time, this idea was getting popular with images. It was still not popular. It was Russian paper was not yet accepted. And that is how I've lost all these years, right? At the time, the code of this was originally in Theano. Imagine, right? Okay. So the idea is you do the skip connection, which helps with this same domain. So that is, you want to minimize the amount of information captured in this bottleneck. And this is what the diagram looks like. Again, there's some math, don't worry about it, but the idea is if you have some input here, before you do all the complex calculations, you also allow the input to bypass that. And that basically takes away some information, right? And then you think, how does this help? It helps because now, like the ensemble network, you have multiple pathways. And the reason we also need multiple pathways is because with the paraphrasing, there's another problem, right? See, there is no true paraphrase of a sentence, right? One sentence, maybe you can replace some word by synonyms, right? But if you take one sentence, if you really had to say the exactly same sentence in different set of words, most time it is not possible unless the sentence is trivial, right? Because they will change, every new word was introduced to mean something which doesn't exist. Right? No two words really mean. Again, I know there are some people who are exporting languages here, and certainly they'll give you a speech at the end these are all blasphemous words, but that is how we think of language, right? Every word is capturing some information, some domain, and the word is not exactly the same. So there are many plausible solutions but not exactly the same. And more importantly, with paraphrasing, you want the model to give you diversity, right? If the same thing was always paraphrased the same way, we are going back to the problem of email where you only have two ways of saying, yeah, fine, thanks, I'll look into it. You want some more diversity. So if your model is taking a sentence, giving you output, you want the model to always give a little bit something different, so that when a friend runs the same model, he gives a different result. Otherwise, we all will end up giving the same replies. So you need diversity in the model. And this thing, sequence models with machine translation doesn't know how to do that. So there's a problem. This is a problem. With translation, there's a perfect single answer, and you will be fine by giving the same answer all the time. With paraphrasing, no. You want to change your output all the time. So we penalize these models for not being diverse. And this also comes by adding skip connections, where because you have multiple pathways, and if you add some stochasticity in that, you will get different results. Again, this curve has so many lines. If you are not colorblind and if you see green line at the bottom, that means it's a success. If you're colorblind, trust me, green line is at the bottom. So it means we did better job compared to, like at the time there were other variants of sequence, including attention, which later on became more useful for the task, but we were able to do better paraphrasing with this. Again, this technique will not do better machine translation, FYI, but for paraphrasing it does. Anyways, so here are some of the examples, like this sentence is paraphrased to this, and a small kitten is sitting in a ball, a cat is curled up in a ball. You can see now these two sentences, they are not exactly paraphrased, right? We replace sitting to curling, and some people will argue it's not the same. But paraphrasers will argue they are the same, and hopefully we are right. So in summary, that's the idea. Some probabilistic algorithms, you want to include some diversity, and adding SIP connections helps with monolingual translations. Okay, and again, like I said, this all, I'm stopping here just for the lack of time, and more importantly, a lot of this work was because of the help of a lot of amazing people, and all of them are here, and some I didn't mention, but you all helped. Thank you very much. But in summary, I want to again say there will be problems with most of the neural networks, and next year there'll be next set of problems. But that should not stop you from seeing where the solution lies. Most of the time, solution lies within the structure. What gives you the problem? All it takes is peeking into it, having some intuitions, trying it. If it works, go celebrate. If it doesn't work, try another idea. Sometimes that's the way to do it. And anyways, there are more details in the thesis, which will be public. All the codes, most of the codes are public of all the papers. I recommend you to try it out. A lot of people have tried it out, and this is research. I hope somebody adds on to this work. Thank you.
Time for a few questions. People want to ask anyone have anything they want to raise for Adi?
One of your graphs in the RePr section seemed to show that you were doing better than the Oracle.
Yeah, absolutely.
So normally when I hear the word Oracle, I think it's the right answer.
So that's why it's a greedy oracle. So maybe the graph doesn't say greedy, but this is actually a very poor man's version of oracle. And I personally think it's not the best way to measure a system. But the only reason we do is because everybody else uses that system to measure. Yeah. Surely we would not do better than a true oracle.
Right.
Other questions? It's okay.
Anything really. It doesn't have to be. If you want to know how to make money using this, email me.
So your image compression thing, with all the perceptual metrics, it performed the same as standard JPEG?
Yes, exactly.
Are there neural perceptual metrics that would take that into account?
So it is. Yeah, that's good. It's an area of research. It's very hard to make a neural network which understands perceptual quality, because by definition, it is something which we understand and we don't know how to codify. People have tried some numerics, but they don't really correlate well, because every time when someone makes a new metric, they get a bunch of people to sit in a room, look at images, and the correlation is not so strong. So unless somebody really makes a perceptual metric which we can measure, it'll be hard to answer that.
But I think most people consider assessing image quality a much harder problem than the compression. Yeah.
Even though it's the same problem.
But so.
I guess it's like a more general academia question.
Sure.
Because I come from software engineering world, and I was trying to find the connection class, or is it like, while I'm waiting for this paper to be submitted, I have some time to kill, so let me solve another big world problem, and while I wait for that one, I will solve the third one?
And so that's a good question. They are very loosely connected with one goal. My goal was to make neural networks available for everyone. Right? Again, that's very hyperbole way of saying make them efficient and make them more robust so that people can rely on it. This is not the final stop. A lot of people have done a lot more work. People will do more work. But connecting goal is democratize neural networks. Right? It is not just for Google and Facebook. Or maybe Microsoft.
Is the pruning process manual that you need a human input to like look at what was inefficient and what you can prune, or can the program do the pruning itself and it doesn't need that initial human input?
So it is mixed. You do need some input. So in the sense, human input is where human says, I will define pruning as this. I mean, you have to determine the criteria, right? So as a teacher, you say, okay, everyone who got less than B failed. So you have to take that initial decision. And once you have decided, then the program can go and check whether they got B or less, and then they will decide. So there is mix. Neural networks cannot on themselves decide if it is a good neuron or a bad neuron.
There's one over here. Oh yeah.
So about the pruning, I mean, so is there any possibility that you can keep the correlations or the useless nodes from arising, and so not instead of pruning them, just keep them from
yes, so that is kind of so it is possible. For example, in this graph, that is what is going on, right? Once they find out the bad neurons, they just stop it. They don't, and that is why, and once you stop the bad neurons, you retrain the rest of it. You get a slightly better performance, but this is not as good as before the pruning, right? Yeah. So again, the answer is mixed. Yes, you will get some performance by gradually pruning out, completely removing them. That way you will get a smaller network. But the secret lies in when people say it's a smaller network, this just means it has a fewer number of variables or parameters. But that doesn't solve anyone's problem.
Yes, I just mean, so is there any way to
keep pruning until you get to 0% of the model?
Like, could you add a loss term to prevent them from becoming correlated in the first place?
Yeah, that's true. And I don't have the graph here, but that is, and we spent a significant time in trying to understand that can we do it as a loss, and turns out you cannot. Why? Because we are trying to do two things. One, we're trying to tell the model to do a good job, and if you penalize the model for being correlation, these two loss functions doesn't work together well. And mostly because of the training techniques we use, SGD or Atom, they are not good at doing these multi-loss optimizations. Therefore, that process fails. In our paper, RePr, you will find a whole section called as orthogonality loss, where we see what happens if we add this as a soft loss and train. It turns out it doesn't do so well. It has to be a hard loss, and it has to be something where you can remove it from the gradient optimization process.
Thank you.
Okay. So with the pruning, I may have missed something, but on that first graph, the goal is to reduce the amount of parameters, but keep your keep your accuracy very high. I'm curious on if you could prune, but actually increase increase your accuracy, right? So you're gonna slowly, almost over time, reduce bad ones, but then add in good ones to make it bigger and raise accuracy from that.
Yes, I think I hit that slide. There is something you can do like that, and turns out small percentage of parameters are such that if you remove them, performance of the model actually improves, right? So, but then most of the time that's not the case. So most of the time, if you remove the parameters, model will degrade. The question is how much and what parameters to remove. That's where a lot of the research is. If you knew right away which parameters, there is possibility that you will get amazing performance all the time, but it is hard to find that parameter. So that function to rank parameters.
So maybe we'll stop there. Thank you very much again.
Thank you.
So by